I will begin. Dear Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right, hopefully I'm awake today. Let us start with a graphing example. Let us graph r equals to 1 minus cosine theta. All right, so to plot this, we will, let's see here. What is this? Can you think of the enveloping curves here? I believe 2 and 0 again, right? This curve's bouncing between 2 and 0. And so essentially it's just minus cosine about the line y equals to 1, right? What's minus cosine look like? You guys can graph minus cosine, right? Something like that. Now we probably don't need all of that, but there it is. That's the graph of minus 1. There's the graph of 1 minus cosine. Now the thing I'm looking at right now, of course, is r this way and theta that way. All right? So we can use such an r theta graph to create the corresponding Cartesian plot for this curve, which is, this curve is given as a polar graph, right? R is equal to a function of theta. Okay, so let me use some color coding here. So I usually look for, as I'm thinking about graphing, I try to think about, well, first of all, I need to label some things, right? So where is this? That's what? That's pi, right? At pi, we have r equals to 2 at pi. And let's see here. Of course, this is 0, right? This is what? 2 pi. As you can see, my inability to maintain a linear scale on graph persists to today. It's not right. Okay. Let's see here. This would be what? Well, let's what's this point here? What's that? Minus pi? All right. Let's see here. Maybe I'd... Where's it hit 0 back here again? Where? Minus 2 pi, right? All right. So let's try to plot this thing. All right, so I'll just focus my attention on like a little piece of it at a time. So let's say we focus our attention on this arc from 0 to, what's this? Pi over 2, right? So that describes, that little blue arc in the r theta graph is going to describe what our curve is going to do between theta equals to 0 and theta equals to pi over 2, right? What happens? It starts at 0, right? And what does it get to by the time it gets to pi over 2? Gets to 1, doesn't it? Suppose that that's 1. And what happens? It starts at 0 and it swings out, right? And so what's that look like? The radius is what? Just kind of something like this, right? Roughly speaking, something like that. Because that's going, again, from theta equals 0 to theta equals pi over 2. You guys with me? Next up, let's go from pi over 2 to pi. I'll do green. Pi over 2 to pi is from here, from the positive y-axis, swinging over to the negative x-axis, right? And what happens? It goes from radius 1, where it starts, right? And then the radius grows to 2. Right, so that's going to do something like this. All right? And then what happens from there? I'll stick with my story of positive angle because it's working. So to go from pi to 3 pi over 2, right? That starts us here, right? 3 pi over 2 is the negative y-axis, right? And where's the final radius here? At 3 pi over 2, it gets back to radius 1 again, right? So there should be sort of a symmetry there. And then what happens in the final little bit there? From 3 pi over 2 to 2 pi, it goes back to 0 again. So, yep.
Why do you go to -1 with the purple line?
-1? What do you mean -1?
I thought it's still at 1 when it's at 3 pi over 2. Why do you go to -1?
It didn't go to -1. What do you mean? This is radius. So this is the graph of radius. So all of the, so it's going to radius. This is radius 2, even though it's where x is -2. So I think, so the heart of your, your question is based on changing the idea of radius and x. But this is r equals to 2, theta equals to pi, right? Which corresponds to this guy. I'll call it Pac-Man. Yep. That's right. If we let theta go on and on and on and think of this as a parametric curve, we're covering this shape like infinitely many times. But certainly going from 0 to 2 pi will cover the whole shape, right? And we could have done differently, right? I mean, you could have started, I think if you went from -pi to pi, that would also get you the full shape, right? I mean, there's any number of different sets of theta you could use to cover the whole shape, the whole curve. All right, let's try another one. Let's say r is equal to, just a second, let me. Trying to find a neat one. Come on. Let's see here. A over b less than 1. Nah. Excuse me. Well, I'm just going to go with something that I think we sort of thought about before, but it's worth thinking about more. Sine of 3 theta. All right. So, relatively simple. I mean, the graph should be pretty pretty much a piece of cake, right? So sine of 3 theta, it just looks like sine, right? Let's see here. But if we go all the way to 2 pi, how many cycles did we go through? We should have gone through 3 cycles, right? If 3 theta, let's see here how to say this. The first, if we set 3 theta equal to 2 pi, that would get us to here, right? So this would be 2 pi over 3. This one over here would be 4 pi over 3. And finally, 2 pi would be 6 pi over 3, right? Now, I'm not sure I need that much of the graph of sine of 3 theta, but that should work. Should work. All right, so now I have my r theta graph, and I can use that to construct the Cartesian graph, right? And I'll use my color coding scheme again. But now we're going to have to think about negative r, not just r, right? So, because some of these are negative, some of these are positive, right? So let's start with the first lobe. What's this angle right here? Mm-hmm. Pi over 3, yeah. So if we look at that, what I like to do is to draw myself a little, so here's pi over 3, right? Here's 0. And that lobe, I mean that node, if you will, in the graph of sine, has to contribute like a petal between these two rays, right? And it sweeps out to 1, where? At pi over 6, right? So pi over 6, right in between those, is where it's longest, yeah? So the graph should be something like that, between 0 and pi over 3. Then next I face this piece right here, between pi over 3 and where? And, yeah.
So when we're graphing sine, cosine, they're different ways of graphing both of them because they're different functions. So like the way you're graphing cosine is different than the way you're graphing sine, correct?
Yeah.
Because you didn't do that method for cosine, and I don't know if it was like just for those functions specifically.
Well, I mean, cosine plus cosine starts at 1 and it drops down to 0 and kind of goes from there. But since this is minus, I flipped it over. And all of that was shifted up by 1 because it's 1 minus cosine theta. So like my thought process is shift up 1 and then graph minus cosine at the 1. But if uncertain, of course, we can always fall back on Desmos at least to get, back up to speed on these sorts of things. Now, between pi over 3, where's 2 pi over 3? I think it's something like this, right? Except the thing is, here we have r less than 0, right? So the rule is that reflects what would be between, see, it would be between 2 pi over 3 and pi over 3, but it gets flipped over down here and gives us this lobe instead. I'll try to. Like that. Because when r is negative, it flips it 180 degrees on the other side. All right? Next, I'll do green. Between 2 pi over 3, and where's this? Pi, thanks. So between 2 pi over 3 and pi, that puts us right in here, right? Let me erase that red 2 pi over 3 there. I don't know. You figure out the color coding that works for you, but that gives us that one, right? And then what happens? It repeats. Is that right? Let's see here. We're going from pi to 4 pi over 3. Like Zach is like, you doubt me? See, pi. Let's see here. This is pi, right? Where's 4 pi over 3? It's this one? But what's the rub? I mean, you might be tempted to say, oh, so I get one in here, right? But yeah, but it's actually it's r less than 0, which means that this is actually the purple one we already drew. So so we go 0, less than or equal to theta, less than or equal to pi. We've covered the whole 3-petaled rose. All right. So thanks, Zach. You are correct. Zach is victorious. It's good. All right. Now, all of this is just a prelude to the calculus we're doing, right? So let me talk about calculus. We talked a little bit about calculus already yesterday. I showed you how to find the slope of a polar curve, right? So there's more we should talk about calculus-wise. So yesterday, we already saw that dy dx was, what was it? Guys, remind me. As a function of theta, it was dr d theta. Okay. Thank you. So we saw that. So that would allow us to calculate the slope. All right. That's one thing. But we could also calculate arc length. What would arc length look like? So remember, our path has parameter theta, right? And so we can write that our cosine theta, our sine theta, where these are both functions of theta, right? So what is that? If we calculate the derivative with respect to theta there, what does that give us? This is not surprising. These are exactly the steps that we did yesterday to derive the slope formula, right? But I'm after something different. I'm after the formula for arc length today. So how do we calculate arc length? Remember? For a parametrized curve, what was our formula? Yeah, like integral over the parameter domain, whatever it is, t1 to t2, square root of, well, we did dr dt dot dr dt. Now, I may have soft-pedaled this formula for you, but what that's saying is you integrate the square root of the speed squared. Like, so we take the velocity vector, and we take the dot product of it with itself to find the magnitude of the velocity vector squared. So I just found the what I'm trying to say is I can calculate the speed squared of the, in this case, dr d theta squared, dr d theta dot dr d theta. Whatever this is, I'm supposed to take the square root of that and integrate to get the arc length. So what is the dot product of dr d theta with dr d theta? That's just a fancy way of saying multiply the x component times the x component. So in this case, we just square the x component and we square the y component. How's that go? What I'm doing is somewhat like one of your homework problems, actually, but your homework problem is a little bit more interesting because there I ask you to look at a parametrization of a polar curve, which is something I have not yet shown you an example of in class. It's not a big deal, though. I'll focus on this, though. So I square it. What happens? We get dr d theta squared, right? Cosine squared theta minus 2r dr d theta cosine theta sine theta plus r squared sine squared theta, and then plus the other term. So that's all from the first one. From the second one, very similarly, we get dr d theta squared sine squared theta plus 2r dr d theta cosine theta sine theta plus r squared cosine squared theta. So beautifully, the cross terms cancel. The cross terms cancel out, right? And we're just left with a pair of sine squared plus cosine squareds. Like this guy with that guy. And you notice we've got cosine squared here, we've got sine squared here, we've got sine squared here, we've got cosine squared here. So this all beautifully simplifies to dr d theta squared plus r squared. So what have I derived? If you go back to how we talked about arc length in terms of parametrized curves, you can see that what we have then is the formula for arc length. Arc length would be the integral from, say, theta 1 to theta 2 of the square root of, well, r squared plus dr d theta. Unless did I drop an r? R. No. Dr d theta squared. D theta. So there you go. This is how we would calculate arc length for a polar graph. So if we wanted to, we could try to calculate the arc length of, like, our examples. Yeah? What would the arc length of example 1 be? What should we integrate? I guess we could integrate from 0 to 2 pi, right? 0 to 2 pi goes all the way around that thing. I think it's called a cardioid. It's kind of like a heart. 0 to 2 pi. The square root. What was r for 1? 1 minus cosine theta. And what was dr d theta? Yeah, plus sine theta, right? Now, just because I can write down an integral to describe the arc length doesn't mean that I can actually calculate that integral, right? Because with the arc length, we're taking the square root of who knows what. If you think back to the start of the course, one of the hard lessons was that, well, we can integrate many things into the square root, not everything, right? I don't know about this one. What is this? Well, thinking ahead, this is going to give me a 1 minus 2 cosine theta plus cosine squared theta. And so I think I end up with something like 2 plus 2 cosine theta. I mean, we might be able to integrate it. I just don't want to try at the moment. Yeah. So in this problem, unless I have engineered the problem to be a reasonable one, all right, it may be that the answer is just what we wrote. The answer might be find an integral which represents the arc length of the polar curve. If that was the question, this is the answer. All right? Example 2, arc length. That's where it gets interesting, right? Because, you know, in this one, because of, you know, the persnickety nature of the negative r, I mean, it's subtle what goes on there. But we should only integrate from what, if we want to get the, I mean, there's various approaches. If you want to find the arc length here, how would you do it? You know how I'd actually do it? I'd use symmetry, yeah. I would calculate the arc length. I'd use by symmetry. I'd say that the arc length is 3 times the integral from what to what? 0 to pi over 3. Bingo. And my r was what? Sine 3 theta, so sine squared 3 theta, and then what? Plus minus 3 cosine 3 theta, quantity squared d theta. Again, I'm scared to calculate that integral because, I mean, if not for the 3, I'd be like, yeah, okay, I can do it. Not a big deal, you know? If the 3 wasn't there, we'd have like a sine squared plus cosine squared. That I can integrate. But with the 3 there, it's sine squared plus 9 cosine. Yeah. Oh, good question. Fortunately, I'm not wrong because it's squared. But, yeah, that was just me being stupid. So, yep.
Where is the arc length? Like, what do you calculate?
What am I calculating? The length, if I took a string and laid it along this purple curve like that, you know, if I could somehow lift this ink and maintain its length and lay it straight, it would be the arc length. But since there's 3 of them, I multiply by 3. Alternatively, you could not multiply by 3 and just integrate from 0 to pi. That would also calculate the arc length of this, right? Okay. What else do we like to do with calculus? We like to find slopes to tangent lines. We like to calculate arc lengths. We like to graph things. This is calculus with analytic geometry, right? There's the analytic geometry part over here, yeah. So the other thing we often try to do in calculus is find areas bounded by curves, right? So how do we calculate area in polar coordinates? So let's say area between polar graphs. So this is the start of a longer discussion. Well, I guess it's really a continuation of a discussion which already began in Calculus 1. How do you find the area between curves, right? I mean, eventually this leads you to the sort of full-blown version of that in Calculus 3, where you learn how to calculate the double integral, which is probably the most robust notion of how to integrate over a flat two-dimensional thing. But this is something in between that and where we were. So here we go. So here's the basic idea. What you're given, all right, is some sort of and then some sort of, I'll make this one easier, like that. I don't know. So the point is, we're going to consider a region where if you start from the origin, right? Draw a ray from origin should hit r in, then r out. All right, so if you look at any ray through the origin, right, there's a clearly defined inner and outer radius. I'll color code them here in a second. So the inner radius I'll make black, and the outer radius I'll make purple. And the question is, and I'm also assuming, and again, this is special to the discussion in Calculus 2. In Calculus 3, we learned how to take integrals over more exotic looking shapes. But, so there's a clearly defined inner and outer radius for the shape, right? And also, we're assuming that we have a clearly defined initial and final angle, all right? So how do you calculate the area of such a thing? So it basically comes back down to this. If you had a, piece of pizza, like so, right? And somebody bit with a perfectly circular bite, like that out of it, right? What's the area of such a sector? What do you need to know to calculate the area of such a sector? Let's suppose that the angle in here is delta theta. And let's suppose that this is the inner radius, and that is the outer radius. What would the formula for the area of such a sector be? Yeah? Yeah, like the area of the entire slice. What would be the area of the entire slice without the bite? I'll remind you, it's 1/2 r out squared delta theta. As a check on my formula, notice what happens when delta theta goes to 2 pi. Right? When delta theta goes to 2 pi, we get the whole circle, right? And you know the area of a circle is pi r squared. And then if you take less than that, it's just proportional to the amount of angle subtended. We need a half because of the way a radian measure works, right? So we want when we put delta theta to 2 pi to get the whole circle. So we know that the formula checks. And then we have to subtract the area of the bite, right? Now, so this is just 1/2 r out squared minus r in squared delta theta, right? And I guess if I want to envision this, I want to envision this as like a little tiny little slice, right? So maybe to be fair, I should add a delta A, you know? This is really just a little change in area, a little bit of the area, right? I'm really envisioning this up here as a delta A. So if we take the sum of all those, what do we get? The net area is approximately the sum, right, of delta AI, I equals 1 to n. If we've partitioned the angle, in, n equal subinterval angles, yeah? So I could spend another 5 minutes of class to make this rigorous, but I hope you see where we're going. And the limit, as n goes to infinity, this becomes an integral, right? The finite sum becomes a continuous sum, the integral. And so I hope I've done enough to motivate to you that the area would be the integral from theta 1 to theta 2 of 1/2 r out squared minus r in squared d theta. This is how we can calculate area using polar coordinates. We did take 1/2 the outer radius squared minus the inner radius squared, integrated over theta. Now this, of course, supposes that your, region looks something like a half-eaten pizza. Although, of course, the outer edge doesn't have to be so regular. It could be something much weirder. But there has to be a clearly defined inner and outer radius for this to make sense, right? Also, negative radius. A little worrisome, yeah. Negative radius is bad because if we're looking at a graph which has a negative radius, then the theta is not the same for the one with a positive radius versus the negative radius, right? Like the same point in the xy graph, if we have positive r, we have theta. If we have negative r at that same point, it corresponds to the theta 180 degrees shifted. So, setting this up with a negative r is you got to be careful how you actually work that out. But let's focus on the less confusing part to start with. Let's calculate the area of just this little bit. How do we do that? What's the area of that? Area in first quadrant, right? Area equals the integral from 0 to pi over 2, right? 1/2 r out squared minus r in squared d theta. How is that going to look for us? What is the inner radius here? I'll blow it up. All right. So if you look at that shape, right? Again, we draw a ray from the origin, and it should hit r in and then r out. There's only r out, right? What do we have to understand in this case? What's r in equal to? Did somebody say 2? I don't think I think that's 0, right? 0. The 2 was in my head, right? Okay. So this is what was a 1 minus cosine theta, right? So we do 1 minus cosine theta, square that thing, d theta. What's that work out to? See, I'm much less scared of asking you guys to calculate areas bounded by polar graphs, right? There's no square root involved. So it's much safer for me to construct these kinds of questions. Where there's a square root involved, ooh. I guess there could be trig substitution, right? But 1 minus 2 cosine theta plus cosine squared theta. So, fine. Remember how that goes? 1/2, 1 plus cosine 2 theta, right? And what's that going to give us? I can do this. I can just integrate now, right? So the 1 integrates to theta, evaluated from 0 to pi over 2, minus 2 sine theta, evaluated from 0 to pi over 2. Oh, man, I should have kept that. Should I distribute the 2 through? I put the 2 out front here. I'll stick with it. So 1/2 theta plus 1/2 sine 2 theta, evaluated from 0 to pi over 2. All of that multiplied by the half out front. How's that work out? So that's giving me pi over 2 for the first thing. This gives me minus 2, because sine of pi over 2 is 1. Then I get a pi over 4 from that second theta piece there. The 0 contributes nothing. The pi over 2 also contributes. This is just straight up. This is worthless in the sense of that just integrates to 0, because it's either giving you a sine of pi or a sine of 0 in the bounds, right? So that piece doesn't matter in that sense. It's all about the theta up here. And so what we got? 1/2 of 3 pi over 4 minus 2, also known as 3 pi over 8 minus 1. Now, again, that just calculates the area in the first quadrant, right? What if we wanted the area inside the whole cardioid? What would we make our bounds of integration in that case? What's that? The whole thing? Whole cardioid integral from 0 to 2 pi, right? The algebra is the same. So we'd have, 1/2, 1 minus 2 cosine theta plus cosine squared theta, d theta. And that integral is actually easier, because what happens when you integrate cosine theta over 2 pi? That integrates to 0 because you're integrating over a full cycle. What's the integral of cosine squared theta over a full 2 pi? Well, sine squared and cosine squared are symmetric over 0 to 2 pi. We know that the integral of sine squared plus cosine squared is the integral of 1 over 2 pi, which is 2 pi. So it stands to reason that the integral of cosine squared over 2 pi is just pi. Of course, you could work through the steps a la the last example. And of course, the 1 integrates to 2 pi. And so what you got is 3 pi over 2. By integration magic. Yes? Like I said, the 2 cosine theta integrates to 0, cosine squared theta integrates to pi, and 1 integrates to 2 pi. So 2 pi plus pi, 3 pi over 2. Now, if you don't like that, if you don't like the way I did that, that's fine. You can always drop back to this kind of calculation, right? Like right here. If you do this and replace the pi over 2 with 2 pi, you'll get the same thing. So, but what I was arguing was just an observation, right? So the integral of d theta from 0 to 2 pi is, of course, the integral of 1, right? That's the integral of cosine squared theta plus sine squared theta d theta, right? So that's the integral of cosine squared theta d theta plus the integral of sine squared theta d theta from 0 to 2 pi, 0 to 2 pi, 0 to 2 pi. And this is straight up 2 pi, right? But the thing is, by symmetry, sine and cosine have the same set of values over a full cycle, right? So if you think about that, the integral of cosine squared and sine squared, they're adding up the same values, just put in a different order. That means that these areas should be equal. And so if these areas are equal to 2 pi, that means that the integral of just one of them is pi. In fact, this argument can be exploited on subintervals of 2 pi to see that the integral of cosine squared and sine squared must be equal on certain subintervals of pi. If you look at a subinterval of 0 to 2 pi and it's such that the values of cosine squared the values that cosine squared takes and the values that sine squared takes are the same, and they're just rearranged. You can cipher that the integrals are equal. This is a trick, but if you're uncomfortable with it, don't use it. You can always fall back on this, yeah, just the details. Excuse me. Questions? What's that? Uh-oh. This question comes with a smile. That worries me.
I don't get on these. So like you said, R was less than 0. So like, and R is greater than 0 on the left graph. So why is it negative? Or like why is it negative less than y on both graphs? Then?
Okay, so R less than 0, right? Well, the red part, the part of this graph that corresponds to that is this red lobe, this red petal. Where is pi over 3 and 2 pi over 3? They're not down here. They're up here. So this, when we have a negative R, we reflect where it would otherwise be. It goes back to the fact that if we have R and theta, that corresponds to minus R and theta plus pi. So if for example, if I have the point R equals to 1, theta equals to pi over 4, this polar point is interchangeable with R equals to minus 1 and theta equals to 5 pi over 4. In the sense that if we put x equals to r cosine theta and y equals to r sine theta, if you plug in this, or if you plug in that, either one into these formulas, they both give us back 1 over root 2 and 1 over root 2, but for different reasons. For the bottom, it's because both cosine and sine are negative 1 over root 2 for 5 pi over 4. That's where cosine and sine are both negative. But then the minus 1 for r cancels that out to give me 1 over root 2. But to be less weird, r equals to 1 and theta equals to pi over 4 also give me 1 over root 2 and 1 over root 2. So like geometrically, the two different polar descriptions, these are two different polar descriptions of that same Cartesian point, 1 over root 2, 1 over root 2. I don't like it. If it was up to me, we would find a way to root out the negative r from everywhere. I think it's stupidly confusing. And honestly, when I do polar coordinates in Calculus 3, I litigiously avoid the use of negative r. Because one of the things we really want for a coordinate system, like long-term in mathematics, what is a coordinate system? It's something that gives a unique description to a point in your space. Like that's what a coordinate system is. If you're a military person, you say, what are the coordinates? You don't want to have a discussion about which ones you're using. You don't want to, the coordinates, of course, there's always a choice of where the origin is, right? I mean, there's always going to be a certain amount of convention involved in choosing coordinates, but anyway. Let's play with Desmos for a couple minutes. I can graph. Graphing by hand is so slow. It's so slow. No internet. What do you mean no internet? It's been open for like, come on. I'm still annoyed. I spent like a good 15 minutes figuring out how to turn off automatic updates on my computer, and somehow Windows has again changed whatever it is that sets the automatic update, so it's doing it again. Oh man, it just irks me. I'm going to go Linux here pretty soon. But then the problem is there's any number of official university this or that I have to do in Microsoft Word or that dreadful SharePoint. You wouldn't know about that. Do you guys know about SharePoint? Good for you. Good for you. Let's hear. I remember using Skype a few years, like a number of years ago, and it was pleasant. Like I just went there, I put in some information, it worked. But then between the time I first used Skype and I secondly used Skype, Microsoft bought it. And then all of a sudden, Skype has to be linked with all my other Microsoft products. It's like, it doesn't matter what my Microsoft ID is. Just let me Skype already. It's horrible. It's horrible. It's horrible. Just horrible. Where was I? No, I don't. Come on. Open. Save this graph. Polar? Question mark? What's going on? Come on. I know you can't see it. I will eventually plug it in. Let's see here. Where is that? Oh, I thought I did something in here. Oh, I remember. I had something in here, and then my computer turned off because Microsoft. And so it's lost. But anyway. So one of the things I wanted to show you guys, let's do some exploring. Let's see here. If we look at something of the form R equal to A plus B cosine. Did someone whisper nerd? I assume that wasn't directed at me. Let's see here. I mean, I'd accept it, but somewhat proudly, I suppose. But let's see here. Look, so that is, let's see here. If A equals to 1, what did we graph a second ago? What was the thing we spent about 10 minutes working through carefully? 1 minus cosine theta? So let me make that B minus 1. Whee! There's minus 1. Go away, software manager. And what happens if we let B be like minus 2? Look at that. So, that would probably be a good exercise for you to work through. Like, try to go through the process we did for example 1 and example 2 for what R equals to 1 minus 2 cosine theta. You should generate something that looks like this. It's got an outer loop and an inner loop. So for a problem like this, you can ask the question, what's the area bounded between the inner and outer loops? Yeah? Maybe we'll do that tomorrow. Let's see here. What happens if I keep going? The loop it's getting worse. Is it ever going to catch up the other one? Maybe not. It looks like it's tending towards like a pair of almost concentric circles, sort of, right? In the limit. I don't know. What happens if we change this? Oh, goodbye. Oh, cardioid. Oh. Circle? Is it a circle? Looks an awful lot like a circle. And then, of course, we could play games. Whee! So this whole family of curves you're looking at, they're called limacons. Well, I'm not sure how to say this. Limacons, perhaps. It's from the Latin word limax, for slug or snail-like creature. So actually, there's a specific case here. I think that's the general term, is a limacon or something like that. But the specific case that we started with in the graph over there is called a cardioid, because it's kind of like a heart. And there's also a dimpled limacon, a convex limacon, A limicon with an inner loop, which you could figure out which one that is. Let's look at a different thing. This is the next thing. Next thing we're going to look at is called a lemon skate, or I'm sure I'm saying that wrong too. But what's that? You read it, lemon Scottie. I like that. Lemon Scottie. Yummy. Let's see here. That's something like r squared equal to. I guess it's a squared cosine 2 theta. Something of this sort of flavor. What? Doesn't like it. Polar equations must be linear in R. Well, that's not true. I just wrote a nonlinear one. It's right here. You know? What's up with that? Fine. I guess we can do the algebra. R equals to what? If R squared was that, what do we have? We have R equal to, whoa. Well, there's the 4 pedal. It would be square root. Ah, no, wrong way. So there we go. Let's see here if we can. Let's what happens if we go from 0 to say pi. It's that part, right? And well, I think we know what's going to happen if we go pi to 2 pi. Like that, right? What happens if we change a? Ah, no. Ooh, oh. Well, that makes sense, right? It's just the size of it, essentially. So a just scales it, makes it bigger, smaller. What would happen if we added b to this thing? Ooh, look at that. Hey, look. It's like untying or tying, isn't it? Whee! I need to make this into a GIF. Or is it a GIF? Whatever. Nobody knows.
I've never done anything sufficient.
My. I was bored the other day. Yeah. Whee! Okay. Oops, sorry. Let's see here. Let's see here. What is the one thing I mentioned that we haven't done yet, but we should do, is a parametrized polar curve. What would that be? What's a parametrized polar curve? What if we did something like r equals to t squared, theta equals to, cosine t? See, this would be an example of a parametrized polar curve. Or you could say, so what does that mean? This is just a slick notation, right, for a very specific kind of path. What does that mean? I mean, how is that interpreted in terms of what we've already done? What would that mean? If you had to give me x as a function of t and y as a function of t,